Good morning. Today we are covering microcytic red cell disorders. So next slide. The next slide. So by the end of this lecture, hopefully you should be able to have defined what microcytosis is, describe the pathogenesis of microcytosis, and discuss the laboratory tests performed in the evaluation of red cell microcytosis. So it's just defining then what causes the microcytosis. We might talk about the common causes. We might talk about a few clinical features before we go into the laboratory tests. When you come back to your third year, then we shall address more into the more clinical aspects. For now, to be basically the basics about microcytosis. Next slide. So when we talk about microcytosis, we are basically talking about the red cell, the red cell morphology. So the red cell is a biconcave cell and has a disc shape with a diameter of between 6.7 to about 7.7, what we call micrometer. It's actually nanometer, not even micro, it's nanometer. So practically the red cell, we estimate the red cell size through a specific measurement that we call the mean corpuscular volume. So we use this parameter to determine what the size of the red cell. Next slide. So the microcytes will basically be cells that are smaller than normal red cells. So you can see micro, there's micro. Micro means smaller. There is macro, which will be covering next week, meaning big or larger. So we are defining micro. Micro means small. Those are basically cells that are smaller than the normal red cells. So the MCV, as I said, that's the one we use to measure the mean corpuscular volume. Normally ranges between 76 to 96. So anything that's below 76 is referred to as microcytosis. So red cells that have an MCV less than lower limit, the lower normal limit of 76 in adults are referred to as microcytes. Next slide. So the microcytic anemias, those are basically anemias that have the red cells which are below the 76 femtoliters of MCV. They are linked by morphologic, meaning the shape. Morphologic means the shape or the size or the way they look like under the microscope. That's the morphology. And the genetic features of deficient hemoglobin synthesis. So everything behind why they're microcytes is because they lack the hemoglobin. Because hemoglobin is the one which is normally found in the middle. So when it shrinks, then the cell also shrinks. That's why it becomes a microcytic, microcyte. And it's often associated with iron deficiency or impaired iron utilization. Generally, that is the main cause because we need iron mainly for the hemoglobin synthesis. So if you lack iron, then you do not develop or synthesize the hemoglobin. So the hallmark of microcytic anemias is basically microcytosis, which means small, and hypochromia. So microcytic anemias are normally referred to as microcytic hypochromic anemia. Why? Because the microcytes, as we said, small, the cells shrink because we reduce hemoglobin, and hypochromia because the area of central pallor is also reduced. Why? Because of the hemoglobin, which has not been synthesized or is deficient. So the hallmark is normally microcytic hypochromic anemias. Next slide. So the degree of microcytosis and hypochromia relate to the severity and duration of the underlying disorder. Yeah, it just means that if the condition has been there for a very long time, or if the deficiency is massive, we have talked about iron deficiency. You don't eat iron for some time at all, or for a long time, then you have very severe microcytic hypochromic anemia. And what we need to know is that microcytic anemias are very prevalent and are clinically important, and it's a must-know lecture because this is what you're going to come across when you become doctors. When you start going to the clinical wards, you'll find a lot of patients with microcytic hypochromic anemias. Next slide. So just a recap a bit. We know that hemoglobin is made of three things. It's made of the iron, it's made of globin, and it's made of the protoporphyrin. Iron is a metal element, globin is a protein, protoporphyrin is an element, also a protein. So all should be provided in optimal amounts in developing the erythrocyte. So if one of them is missing, if iron is missing, then you have deranged hemoglobin synthesis. You have the globin missing, the same. You have protoporphyrin missing, you have the same. So we shall go through this just to show the pathogenesis of how hemoglobin synthesis is affected. Next slide. So we talk about the pathogenesis. Remember, we said that our objectives was to define. We have defined microcytosis. We're going to talk about the pathogenesis. So when we classify the pathogenesis or the causes of microcytic anemias, they either do, as I said above, do the disorders of the iron metabolism, disorders of the globin synthesis, disorders of the porphyrin, and the heme is that's the protoporphyrin that we talked about. So any disorder in any of those three things will cause an abnormal cell, which is a microcytic hypochromic cell. Next slide. So we should start with the disorders of iron metabolism. So what can go wrong with iron, to cause this? So you can either have iron deficiency anemias, which means you are not having enough iron in your diet. We shall be talking later about how you get iron, how you eat iron in your food, either from the vegetables or from the meat products. That's one cause. Or anemia of chronic disorders, which means that a person has been sick for a long time, so they're not able to utilize the iron that they eat from the diet, for example. So those are the common causes of iron metabolism. So the above are amongst the most common cause of microcytosis. But others are if you have a problem of transferring anemia, what we call a transferinemia. So this is an autosomal recessive trait that's inherited, where for some reason, when you eat food containing iron, that iron is converted in the GI system, is absorbed, the jejunum. Once it's absorbed, it's unable to be transferred, because it needs to be transferred to the relevant organs for it now to be incorporating the red cells. If it's not done that way, then you cannot have, it's not being used. So you have microcytosis. So that's one of the causes of impaired iron metabolism. The other one is a rare familial microcytic anemia, where it's a normal condition. You just find people with microcytic anemia. yeah, but it's not pathologic as such. If you have patients who have gallium, who had administered gallium, gallium is some chemicals used for treatment of some conditions. Gallium has been shown to bind to iron. So when it binds to iron, it means that that iron is not available to be used by the system. So those are the causes: iron deficiency anemia, anemia of chronic disorders, transfusionemia, rare familial microcytic anemias, gallium administration. Those are disorders of iron metabolism. Next slide. So you can also have the disorders of iron met pathway, meaning we know that transferrin, iron is the main source of iron for hemoglobin production in the red cells. So if you have iron deficiency, so in this what we've just talked about, the main thing is that there's no availability of the transferrin. Transferrin is the storage form. Yeah, is the transfer form, the one being transferred, as I said. Transfer, you have iron absorbed in the GI is transferred to the cell, to the red cell, so it can be incorporated in formation of the hemoglobin. So in iron deficiency, what you have is reduced transferrin saturation because not able to transport the iron, it's not enough. So you have reduced hemoglobin production. You have a microcytic hypochromic anemia. That's how the process occurs. So it's just the transferring of the iron from the absorbed form, that's the iron, the Fe2+, into the iron that's required for metabolism of the formation of the hemoglobin. Next slide. So that was disorders due to lack of iron. So disorders of globin synthesis. So globin, as we said, as you know, is basically is a protein. Is which forms part of the hemoglobin, the chains that you find in the hemoglobin. So the disorders of globin synthesis can be, one is due to thalassemia. We know thalassemia is a condition where you either lack or reduced production of the globin chains. It's either reduced or complete lack of the globin chain. So you don't have the globin chain, then you can't have hemoglobin synthesized. It's reduced. Yeah. Conditions like unstable hemoglobin diseases, hemoglobin E disease, or hemoglobin E trait, hemoglobin C disease. So they're basically abnormality in the globin synthesis, so thalassemias, hemoglobin E, hemoglobin C. Next slide. Next slide. So in thalassemias, it's basically a group of inherited disorders in which there's synthesis of one of the normal polypeptide chains of globin is deficient. So if you read about the structure of the hemoglobin chain, I mean the hemoglobin, you have normally either four globin chains, and you have two betas, two alphas. Yeah. So if one of them is missing, two betas, there's alpha, there's beta, there's sigma. It is depending on the type of hemoglobin you're talking about. But if you talk about the normal A, one is alpha and beta. So if one of them is missing, either a complete one of the chains, instead of having the four chains, you have three chains. Or if you have, instead of the four, you have two chains, or you have one. Of course, then you have reduced hemoglobin globin synthesis. That would affect the hemoglobin. So the hemoglobin deficiency is either due to defective synthesis of a polypeptide chain, yeah, e.g. in beta thal, you have the beta chain deficiency, yeah, an example. Alpha thalassemia, you have the alpha chain deficiency. So the complementary chain formed in excess is normally moved in the spleen. So you find that these patients have microcytic hypochromic anemias because they do not have enough globin in their hemoglobin. Next slide. So this just relating that, for example, in a stable hemoglobin disease, the hemoglobin is formed, but it is abnormal. When it's abnormal, the spleen, which normally cleans the body, cleans the red cells. Yeah, it does. So it removes it, thinking that this is an abnormal cell or abnormal substance or chemical. They may remove it. So when that happens, then of course, what comes out in the blood system is reduced hemoglobin, hemoglobin that lacks the globin chain. So you'll have, of course, microcytic hypochromic anemias. Next slide. So disorders of heme synthesis and the porphyrin, as well as that was the third component. We had the iron, we had the globin, we had the protoporphyrin. This is seen in sideroblastic anemias. So here there's defective ALA synthesis, e.g. vitamin B6 deficiency, some drugs, some toxins can lead to that. In lead poisoning, you have this, the porphyrin molecule is not formed. Some hematological conditions like leukemias, you have a deficiency of heme synthetase, that's an enzyme that's supposed to help in the synthesis of the hemoglobin. Deficiency of copopyrinogen oxidase. So these are basically enzymes, the ALA, the heme synthetase, copopyrinogen oxidase are basically enzymes that are responsible for the formation of the protoporphyrin. Yeah. So if you have that, especially things like lead poisoning, so lead poisoning affects this pathway. Yeah, it blocks, just where, as we said, gallium up there. Gallium was affecting the absorption of iron, or it binds to iron. The same thing with the lead. Lead poisoning will affect the synthesis of this. So the end product is you have what you call sideroblastic anemias. Yeah. So sideroblastic anemias is one of the causes of a microcytic hypochromic anemia. Next slide. So sideroblastic anemias, just to quickly talk about it, is characterized by ringed sideroblast in the bone marrow. So when you look at the bone marrow, we do a bone marrow aspirate, we stain the slides. What we find is the immature red cells, or the precursors of the red cells. Yeah, we have a ring of iron basically deposited around the, you think about the red cells around normally, you have the in between, you have the nucleus. In immature cells, you have nucleus, you create the red cells. So around that, you'll find a ring of deposition, around, so they're developed pneumoblasts with pathologic iron deposition in the mitochondria around the nucleus. So you have the nucleus, you have the red cell, you have the nucleus. So around it, you have iron deposited. That's what we call the ringed sideroblast. And sideroblastic anemias can be inherited or acquired. Acquired is in cases, for example, like iron in lead poisoning. You acquire that, but can also be inherited where you have any of those enzymes lacking as an inherited condition. The next slide. So before I go into this, so I will summarize. We have defined microcytic hypochromic anemias. We have defined them as cells that are below MCV of 76. We have defined the causes. Broadly, we've said due to iron deficiency, due to globin synthesis deficiency, or to protoporphyrin. So if you put all those and you are asked a question, what are the common causes of microcytic hypochromic anemias? One, it will be iron deficiency, lack of iron. Two, thalassemias, as hemoglobin, the globin chain synthesis. Three, sideroblastic anemias, we mentioned that, the protoporphyrin. Four, lead poisoning, gallium poisoning. Those are some of the common causes, if you have to ask such a question. So how do we evaluate microcytic hypochromic in the laboratory? So next slide. So and then test to distinguish between the three major disorders of the group, either iron deficient or anemia of chronic disease, thalassemias, or the protoporphyrin. Next slide. So test to define or to confirm that these are microcytic hypochromic anemias. The first thing is to do a full blood count. Yeah? That's basically a full hemogram or total blood count, whichever name you use. Here we are looking for basically reduced hemoglobin. When you have reduced hemoglobin, you have accompanying reduced hematocrit or packed cell volume, because the red cells are fewer, so they'll be reduced, or they'll be reduced red blood cell counts. Yeah, so that's the first one. Just this shows as anemia. And then you have reduced MCV, the mean corpuscular volume, reduced MCH, mean corpuscular hemoglobin, and MCHC, mean corpuscular hemoglobin concentration. So these are variables we use. Now this one will tell us if it's the MCV is below 76, if the MCH is reduced below 32, MCHC, I can't remember the amount, but if they reduce below the normal reference range, then we confirm this is a microcytic anemia. So we already know anemia up there, this is microcytic. The white cell platelets will be variable depending. Normally you find platelets are increased in iron deficiency for some reason, they're increased, but that's variable depending. The most important is, oh, sorry. Thank you, okay, fine. I'll go slowly, sorry for that. Be free to ask me if you need me to repeat. I can go back and repeat. If there's anything for me to clarify, I can go back. So let me start again, let me repeat. So we said that the test you want to do for laboratory evaluation is to confirm the anemia, confirm microcytic hypochromic anemia. Then the other level of test is to actually now see the cause, either iron deficiency or thalassemias. So we'll go through that to see which test you need to do to evaluate any of those. So we start with the full blood count. In full blood count, we said you do the reduction in there's reduction in hemoglobin. Hemoglobin is reduced, hematocrit is reduced, the red blood cell count is reduced, showing that there's anemia. Then you have reduced MCV, reduced MCH, reduced MCHC, showing that it's a microcytic anemia. The white cells, the platelets will be variable, they don't matter. So this first picture, when you're given that full hemogram or given that total blood count, when you look at it, you should be able to say this is a microcytic hypochromic anemia using these parameters. The next level of test is what we call a peripheral blood film. A peripheral blood film. So a peripheral blood film is basically we get the blood from the patients in an EDTA bottle, then we put it, we spread it on a slide, and then now stain it. After we stain it, then you look at it under the microscope. Yeah. So we are actually looking at the morphology. Remember, we talked about morphology up there. So here is the red cell morphology where we'll see the microcytes. We shall see the hypochromia. We will see the anisocytosis. And anisocytosis means the different sizes. They won't be uniform. They won't be all the same size. There'll be normal ones, might be big ones, but predominantly in microcytic hypochromic anemia, you see mainly microcytes and hypochromic cells, mainly. And then you have poikilocytosis. Poikilo means different shapes. So anitho means size, different size. Poikilo, different shapes. So you have what we call anisopoikilocytosis. Different sizes, different shapes. Yeah, we shall see some of these as we continue with your lectures. Next slide. So this is how to look. Yeah. So if I use this as an example, those small ones, pink cells, as you can see there, pink, with a central area of pallor, those are the red cells. Yeah. The pink ones with a central area of pallor are the red cells. The cells that are purplish with the lobes inside, these are neutrophils. Yeah, you can see like two lobes. The cell down there that is purplish, but almost round, with a purplish round with a little cytoplasm on the surface, on the surrounding it, are lymphocytes. So you have the red cells, you have the neutrophils, you have the lymphocytes. And then you have the platelets, the small dotted ones, purple dots that you can see spread all over. Those are the purple, those are the platelets. So if you look at the red cells here, one thing you can notice is that they're small, they're microcytic. So microcytic is in comparison to the lymphocyte. The lymphocyte down there, where there's an arrow, almost an arrow showing the next to that arrow, you go up a bit. Yeah, that's a lymphocyte. Can the class rep show where the lymphocyte is? I'll go down. Lymphocyte. Let me see if you know where the lymphocyte. That one. That's a lymphocyte. There are two of them. Those are lymphocytes. So that's what we use to measure morphologically the size of our red cell. So you can see the red cell are smaller than the lymphocyte. So the in addition, this one is a part. There's also no hemoglobin. So that is why they are microcytic hypochromic cells. Next slide. Then before you move there, the other thing you notice, I don't know if this is very clear. This is not clear. Okay, you are supposed to see some teardrops, see some oval cells, see some banana cells, you know, what you call poikilocytosis. Yeah, different shapes. If that's it's not apparent in this slide. Next slide. So that is the initial test. So you as we said, first test is to do a total blood count. I've already said that, plus a peripheral blood film. So that will confirm to you that this is a microcytic hypochromic anemia. The next is to ask yourself then, what is causing this microcytic hypochromic anemia? Yeah. That's why we say now you do tests specifically for defining iron deficiency, defining thalassemia, abnormality or deficiency, the grouping chain, that's deficiency, then also define the protoporphyrin deficiency. So for iron deficiency, what do you want to do? You want to check for serum iron levels, they will be reduced, and check for the serum ferritin. Ferritin is the storage form of iron in both the liver and in the bone marrow. Yeah. you check for the storage, it will be reduced. The transferring saturation will also be reduced. Remember, we talked about transferring saturation up there as a part of the pathogenesis of iron deficiency. Yeah? We talked about it. The total iron binding capacity will normally be increased. Yeah, because the capacity binding, because there's not enough iron in the body, the binding capacity will be increased. It's ready to absorb more iron. That's what it means. The serum transferring receptors will also be increased because they're waiting to absorb more transferring. You can also do the erythrocytes protoporphyrin, zinc protoporphyrin, because this is part of this is a component that's important in the formation of the iron that is found in the hemoglobin. So those are the biochemical features, the test you're going to do to check whether you have iron deficiency or abnormality in metabolism of the iron. Next slide. You can do the bone marrow aspirate. We rarely do bone marrow aspirate in straightforward iron deficiency. In a straightforward iron deficiency, please don't do a bone marrow aspirate. But the situations where you do a bone marrow aspirate, for example, in anemia of chronic disease, because there could be other causes that can be found or detected from the bone marrow. So in the bone marrow, we normally stain the marrow, we stain it. So we collect the marrow. Once we collect it, we spread it on the slide, we put on the slide, then we stain it. Yeah? We stain it with a special stain called the Pars stain or the Prussian blue stain. And this one stains for the iron. So in absent iron stores in the bone marrow, the Pars stain will not be detected. Yeah, because the Pars stain is supposed to detect the iron. That's supposed to do. Remember we said the iron is stored in the bone marrow or in the liver. So we're taking the bone marrow, we are staining to check if there's any ferritin or stored iron in that marrow. Next slide. Then before we go in that, we talk about sideroblastic anemias. We said in sideroblastic anemias, you have the cells around the nucleus. There's a ring of iron deposition. That's what we said. So in a bone marrow, you'll be able to detect those sideroblastic anemia or iron deficiency because of lack of iron in the storage form in the bone marrow. So this just shows that. So in Pars stain, yeah, we stain the marrow, and normally, as you can see down there is the normal iron stains, iron stores. You can see the blue colors, yeah, the bluish coloring, which shows that there's enough iron in the marrow. Up there, you can see almost no bluish, just very little. So it's reduced iron stores. So that's what we do. We look at that under the microscope, and we're able to define and say that we do not have enough iron stores in the marrow. Next slide. These are the ringed, we talk about the ringed sideroblasts, as you can see. You have that as a normal blast or not immature, but a precursor of the red cell. So the precursor of the red cell is normally has a nucleus before it goes to the peripheral blood, where it's nucleated. But within the bone marrow, it has a nucleus. You can see that, yeah, it's a nucleus. Then so you can see around it, that ring of iron deposited around it. That's called the ringed sideroblasts. So you find them in sideroblastic anemias. The next slide. So this is, you use the same stain, the Pars stain, to detect that iron. Good. And I think that should be the end of our lecture. So if I summarize for those who came in late and for those whom I was too fast for, if I summarize very, very briefly, we defined microcytic hypochromic anemias. We define them as red cells that are below the size of 6.7 nanometers. Yeah, is nanometers, I think, nanometers. Remember you said the normal size is between 6.7 to 7.7. But in the laboratory, we use what we call the MCV, the mean corpuscular volume, to help us. So the normal MCV is between 76 and 96. Anything below 76 refers to as microcytic. Between 76 and 96 is normocytic. Above 96 is macrocytic. So microcytic hypochromic anemias will be less than 76 femtoliters. Yeah. And microcytosis normally accompanied with hypochromia, because the end result of microcytic hypochromic and microcytic anemias is there's no formation of the hemoglobin. That's the end result. And we say the causes are either reduced iron metabolism, globin chain formation, or the protoporphyrin formation. So those three things are those which form the hemoglobin. They come together and form the hemoglobin. So if you are lacking any of those, then you have reduced hemoglobin. And you have reduced hemoglobin, then you have hypochromia. That's why we refer to these anemias as microcytic hypochromic anemias. So then we talked about the causes of those iron deficiency, iron metabolism, the globin synthesis, and the protoporphyrin. We give examples of iron metabolic, lack of iron in the diet, chronic disease. Yeah. We talked about other conditions like gallium that cause iron metabolism to be affected. Globin, we talked about the chains, thalassemias mainly. We talked about the thalassemias. We talked about the unstable hemoglobins, yeah, hemoglobin E, C, yeah, because those mean you're not forming enough globin. Thalassemias, we said thalassemias are basically reduced production or weight of the chains, either beta chains or alpha chains. Yeah. So having the 4 chains, you have 3 or 2. They're reduced basically. Yeah. And then the protoporphyrin, we talk about the abnormality of the enzymes like the ALA synthetase. Yeah. We talk about the lead poisoning. We talk about sideroblastic anemias. So that was basically what we said on the protoporphyrin. Then now we talk about the laboratory investigation. We said you do the total blood count first. Then you do, you're not sharing the screen. I'm just talking. I'm just revising. I'm just going through what you've just gone through. Okay. Yes. So yes, I said we do the total blood count. We do a peripheral blood film. Total blood count. You find the reduced hemoglobin, reduced red cell count, reduced hematocrit. Then the MCV, the mean corpuscular volume, will be reduced. So that tells us this is a microcytic hypochromic anemia. Yeah. Then we can do a bone marrow aspirate. I mean a peripheral blood film first, just for the morphology, and I showed you the morphology. Yeah, you have the microcytes. The microcytes are normally smaller than the lymphocyte. Yeah, I showed you the lymphocyte, and the accompanying red cell is smaller than the lymphocyte, and the accompanying hypochromia. Yeah, less than a third of the pallor of the red cell. That's all microcytic hypochromic cells. And then the other test is a bone marrow aspirate. Bone marrow aspirate, we said you use it to assess the iron stored in the marrow. Yeah, so you can using the Prussian blue stain. If it's reduced, then you confirm that this is iron deficiency. Yeah, if you find the ringed sideroblasts where there's iron deposited around the nucleus, those are called ringed sideroblasts. and that's tested as sideroblastic anemia, which is also part of the microcytic hypochromic anemias. And then we talked about the iron deficiency, how you take check for serum iron, you check for total iron binding capacity, the transferrin levels, all those. Yeah. Then finally, the others. Yeah. But for sideroblastic, the protoporphyrin also lacking in the system. So that's what we basically covered this morning. Thank you so much. Any questions for me? Any questions for me?
I think there are no questions, sir.
Okay, fine. So have a good day. Thank you so much.